So I'm going to present the historic concrete conservation with nanomaterials, and I will speak about the concrete decay and the design of products that could be applied for the conservation of the concrete, ways of application and assessment, and some conclusions. The major part of my presentations derives from an Horizon project in which multifunctional tailored treatments that could incorporate additional performances like super hydrophobicity and corrosion inhibition were developed. And the main approach in this Horizon project was to provide some impregnation new products which could produce the same calcium silicate hydrated gel that is produced during the cement hydration. And therefore, this gel that is responsible for the engineering properties of the cement paste to be reinforced and conserved with those new products. So before going to the design of those specific products that we have applied and we have tested, I would like to show you some details on the concrete composition, the characteristics, and the decay forms. When we are speaking of concrete, we need to know that the main two components that we find in the concrete are the cement paste and the aggregates. The aggregates can be usually classified in two groups, which two groups are of fine and coarse diameter, and they more or less occupied about the 60 up to 80% of the volume of concrete. The paste is composed of cement, and of course water was added, and some other supplementary cementitious materials like the pozzolans, some specific chemical admixture that function as improvements of basic properties of concrete. And in the concrete design and production, we have to have in mind that a well-graded aggregate with low void contents is desired for the efficient use of the paste. And in this mix, each aggregate particle is completely coated with a paste, and the space between the aggregate particles, of course, is completely filled with the paste. So, the quality of concrete is greatly dependent upon the quality of the paste, and an important factor that determines this quality of concrete is the water to cement ratio that is used. And this water that was added created the hydration of the cement, which takes place very rapidly at first, and then more slowly for a longer period, according to the exterior conditions. For example, humidity here plays an important role. It is important to underline here that the paste, if the paste is thinned with water, then its quality is lowered, and this has an impact of the strength of concrete, and therefore the concrete became less resistant to weathering. So it is essential for a concrete with a high quality to have a proper proportion of water to cement. Going on with the main components that are formed during the cement hydration and the cement production, we need here to evidence that there are four main formulas: the tricalcium silicates, dicalcium silicates, tricalcium aluminates, and tetracalcium aluminoferrite. Here you may see some structures under the microscope of those formulas. But what is very important here to understand is that after the hydration of the Portland cement and the production and the formation of this calcium silicate hydrated gel, what is important to understand is that we have this complex structure in which there are the main bonds of silicon with the oxygen and the calcium atoms that are interpolated within this structure. The structure of the final gel is important to take into account because the products that we will produce and then we'll apply it for the cement and the concrete conservation should be compatible with this structure. Indeed, here there is another image of the product that we have designed, and you may see the similarities between the calcium silicate hydrated gel of cement and the structure that is produced. I'm going to explain it in detail in the other slides that follow. Here, I would like to evidence some causes of decay of the concrete, which make the interventions as an indispensable step when dealing with concrete, not only historic concrete, but even with the modern constructions with concrete. We have an expansion of corrosion products because of the steel reinforced bars that are found in the concrete and especially in the reinforced concrete. Then we have problems with the freezing of trapped water that create stress, and therefore a lot of fissures were developed. The fire or radiant heat have an impact on the concrete structure, the aggregate expansion also, and of course other causes of decay are the seawater effects, the bacterial corrosion, the leaching of the surface and even in depth sometimes, the erosion by fast-flowing water, physical and chemical damage from carbonation, chlorides, sulfates, and water. Here in this image, you may see a typical crack pattern that is associated with the so-called alkali-silica reaction that takes place between the gel of cement that is in the concrete and some specific aggregates that contain formulas of silica that are reactive with this gel. And of course here, the degraded concrete and rusted exposed to the environmental weathering when we are dealing with structures in bridges, like here we are in the Niagara Falls, and therefore we have this corrosion of the reinforcing bars. In this image, you may see also other decay patterns. Here we have the efflorescence that is formed on the concrete surface, and we may say here that this is not the most harmful decay form, because we have an aesthetical alteration of the concrete, but what is important here is that efflorescence is almost associated with subefflorescence. This means that salts could also crystallize inside the structure of concrete. And therefore, the greater volume that is created after those salt crystallization creates some fissures and therefore deteriorates concrete a lot. Here is the case, for example. In this image, you may see the stalactites growing beneath a concrete structure as a result of the calcium carbonate dissolution and reprecipitation, another decay factor of concrete. And of course, there are severe decay when the concrete structure are undergoing this freeze-thaw deterioration of concrete. Therefore, it is well known that in order to protect concrete, even modern concrete, a lot of coatings were proposed, and those coatings are cementitious waterproofing membranes, can be of two components. This means that we have a thixotropic material in a cementitious modifying polymer coating, and this coating is applied on the surface of concrete and therefore prevents from the aggressive effect of acid gas, moisture, chlorides, and resist to chemical attack. Of course, a lot of efforts have been done up to now in order to produce as much as possible flexible, breathable, and easy to mix and place waterproof membranes. And the concept of applying a breathable coating is important not only in the structures of historic significance, but even in the modern construction, because the most moisture that is entrapped inside the building could create a lot of deterioration effects and could initiate a series of reactions between salts and dissolving all the main compounds that the building is consisted of. One, of course, of the drawbacks of those coatings that were proposed for the modern concrete maintenance is that when they applied, they totally changed the appearance of the surface, and therefore, in order to protect the historic concrete, we have to design some coatings which do not alter the aesthetic parameters of this concrete surface. Here you may see some groups of polymer coatings, of polymer clay, of cementitious coatings, and geopolymers that have been used up to now. Impregnation treatments could include silicate-based solutions like lithium, calcium, sodium silicates, and fluorosilicates, or even nanosilica and nanomagnesium oxide composites. The ethosilians, which are based on the ethyl silicates, is a group of materials that is proposed for the protection of concrete, and of course some bacteria that can induce the production of calcium carbonate and sometimes even the silica content of the concrete. What is the main problem with all these coatings that have been applied during different processes are the low penetration depths and in the efforts to approach the conservation of the historic concrete monuments. and buildings, what is important is to propose coatings with a high penetration depth and and coatings that could preserve the aesthetic qualities of the historic buildings, and not only that, but to have also some other multifunctional properties like superhydrophobicity, corrosion inhibition, and, if it is possible, even the self-healing performance. Therefore, one of the main objectives of this Horizon project that finished in 2022 for the conservation of the 20th century cultural heritage of concrete was to propose some impregnation treatments. You may see here that when they applied on the surface could produce this super hydrophobic effect, and of course how to combine this hydrophobicity with the corrosion inhibition, because a major problem and a major issue when dealing with reinforced concrete is to be able to protect the steel bars that are inside this concrete, and it would be a beneficial effect to have a product that could combine both the hydrophobicity and the corrosion inhibition. But in order to be able to explain in the best way which is the concept behind the design of those new impregnation treatments, I would like to show you some schematic images here on the production of the nanomaterials that are based on the so-called sol gel process. So in the sol gel process, we have a dispersion, we have a colloidal solution through condensation and gelation. We can have different products here. After the first gelation, which is derived after the evaporation of the solvent, we have those two gels, exerogel, that is a very condensed structure, and then after gritting we can also have the powder that is derived from this xerogel, or in other conditions of supercritical drying. This means that we have a very rapid evaporation of the solvent here. Aerogels are produced, which then can seeder and yield dense ceramic materials. Those steps are very important in the chemistry of the sol gel process, because products like aerogel and dense ceramic materials have a lot of applications in the material sector, and of course, especially the aerogel impact on the production of insulation products is very important nowadays. And a lot of efforts have been done up to now to produce the best and effective and cost-effective aerogels for incorporated them in the design of the insulation products. Here from the colloid sol, we can also have fibers. We can also have with drying again powder, and of course this colloidal solution can be applied on for coating different substrates, and then they can produce a dense thin film. In our case, we are in this situation here. We can apply our products on the surface of concrete, and of course, after penetration of this colloidal solution inside the concrete structure, we can also have the xerogel formation, which is important in order to reinforce the decayed concrete grains. So, the precursor material for the salt gel process and the products that are derived for the application of the conservation of concrete structure is this one, the so-called tetraethyl silicate, in which we have a structure with an atom of silicon and then those four bonds with oxygen and ethyl groups. According to hydrolysis and polymerization of those monomers, we can have the final xerogel product. But there is a great drawback with these products. The great drawback is that after the solvent evaporation inside the pores of the concrete, here we have a system of pores of concrete in which the colloidal solution has been applied. You may see here that after the solvent evaporation, different meniscus are formed, and there is a difference in the height inside the pore solution. Therefore, according to this equation here, a pressure is generated, and this pressure is responsible for the cracking that is observed with the gel formation inside the pore. Therefore, instead of having a compact and stable product, we have a product with a lot of fissures. And all the attempts up to now is how to intervene and minimize this difference in pressure here in order to obtain at the end and to have a gel that could resist this cracking formation, which is an inherent process during the salt gel formation. In our lab, we have studied a lot of stable layers on monuments, the so-called patina layers. We can find those layers in monuments like Parthenon and in other Mediterranean monuments. And we were very curious about the stability of those layers and how those layers were able to protect the substrate of the monuments. Therefore, after a lot of analysis, we have found that this stable structure shows two main components. One is the silica, and the other one is a structure that is called calcium oxalate, and this is produced from the decay of previous treatments that deteriorate with organic substances like linoleum oils, like white eggs and so on, that give these radicals of oxalate, and those radicals react with calcium and produce the calcium oxalate. We also find in those coatings a lot of silica because those coatings were applied with a silica powder and a binder, which is the oil, an organic substance, and after transformation, this gives this calcium oxalate anion. So, according to the analysis of these stable layers on monuments, we have thought how to produce those stable layers in lab, but in the form of an impregnation colloidal solution, this is indispensable and would help to apply this colloidal solution to the surface of concrete, and therefore, after that, the surface of concrete could be protected. Indeed, we started with a one-pot synthesis in which the ethyl silicate initial raw material was incorporated with calcium, with nanocalcium oxalate, that is produced with another salt gel process. And after the mixing of those two colloidal solutions, we have at the end, and after 22 days of gelation, this xerogel, which was without cracking, and the analysis demonstrated that calcium oxalate was incorporated in this structure of the silica oxygen network, and of course this product, which is very similar to the gel produced during the cement, could be combined and derive another product very compatible to the concrete gel structure. So after the application, we will have a reinforcement and an enhancement of the concrete structure. This is also demonstrated by the infrared spectrum here, in which bonds of the silica and the oxalate incorporation was evidenced, and even in those structures under the scanning electron microscope, in which there were very obvious the links between the product and the cement grain. Indeed, here you may see the untreated cement and how the treated cement created those breaches with the grains of concrete. And of course, you may see here that the structures were without cracking instead of the initial TEO structure, which alone and without the incorporation of calcium oxalate shows those crackings. Of course, after the application, we have tried to assess if the structure was reinforced, and according to a peeling test, we have seen that less material was removed after the application of our product comparing to the initial removal material. And this could be explained, as we may see here, because of the enhancement of the hydration in the very early days, comparing to the carbonation that was continued and have more or less the same values with the product without the treatment that was applied. It is important to show here another aspect of this application. A concrete that was deteriorated and aged with the freeze-thaw application, and the creation of those cracks, you may see that after the application of the treatment shows a complete filling of these crackings, and not only that, but a self-healing effect in which more carbonated structures were produced after passing some time and filling those cracks that were produced. Indeed, studying the chromatic variation, they are not a chromatic, there was an acceptance chromatic variations according to the rules that are imposed in the cultural conservation of and application of those products. And finally, another issue that was achieved with this product is the incorporation of this impregnation solution with some anti-corrosion molecules that could be released through those structures and incorporated to the initial structure of our product. And this release of those anti-corrosion agents, which was evident after the application of the consolidation treatments, protected even this bar of concrete and could be proposed and used as a multifunctional treatment, because with one product you can have the hydrophobic protection of the concrete, the consolidation effect, which is responsible for the reinforcement of the grains of concrete, and of course the release of the anti-corrosion agents on the surface of bar that could protect this bar from further deterioration and corrosion of the concrete. So my conclusions, we have developed long-lasting, practical and affordable conservation products and techniques for the preservation of concrete structures. And this effective consolidation was achieved by producing in situ those products and the calcium silicate hydrate gels by applying them on the surface of concrete with a penetration depth greater than or equal to 20 millimeters. This consolidation increased the mechanical properties of the decayed concrete by over 50% and healed the cracks until 0.5 millimeters of width, and innovative corrosion inhibitors specifically developed could be incorporated in this consolidant composites, and they participated as chemical moieties that functionalize the new calcium silicate hydrate gel structure. So the products developed will provide long-lasting structures to the future generation by preserving the sustainability and durability and keeping the legacy of the technological achievements from structures like Pantheon. Thank you very much for your attention, and allow me to show a book that we have published in 2022 regarding the conservation of stone heritage and the traditional and innovative materials and techniques. I will be glad to answer to your questions and
yes,
your
first
comments.
of all, thank